There is a difference between what cannot exist and what should not exist. The universe does not forbid outcomes. It does not choose. It operates through forces that emerged in the first fractions of a second, fields and particles and symmetries that have shaped every galaxy, every star, every atom across 13.8 billion years. These rules are not written. They are encoded in the fabric of space itself, invisible architects that determine what can form, how massive it can become, and how long it can endure. We observe their consequences everywhere we look. We map their effects across cosmic distance and time. And for the most part, they appear consistent. But consistency is not the same as completeness. Somewhere in the observable universe, separated from us by distances so extreme that light itself has spent billions of years crossing the void, there exists an object whose presence challenges something fundamental. Not because it defies a single law, not because it violates one prediction, but because its mere existence suggests that our understanding of how structure forms, how matter behaves under gravity, and how the early universe evolved may be incomplete in ways we have not yet grasped. This is not about impossibility. This is about confronting an object that fits uncomfortably into the framework we have built. A framework constructed from decades of observation, mathematics, and physical reasoning. It is about standing at the edge of what we believe the universe permits and finding something that forces us to reconsider the boundaries themselves. To understand why this object should not be in our universe, we must first understand what should be possible. The universe began in a state of extraordinary uniformity. In the moments after the Big Bang, energy and matter were distributed with almost perfect smoothness across all of space. The temperature was so high that particles could not yet form stable structures. Photons, quarks, and electrons moved through an opaque plasma, colliding endlessly, preventing the formation of anything resembling the organized cosmos we inhabit today. This phase lasted hundreds of thousands of years, a cosmic childhood during which the universe expanded and cooled, but remained featureless. Then gravity began to act on the smallest irregularities. These irregularities were not random. They were quantum fluctuations, density variations imprinted during the inflationary epoch, stretched to cosmic scales by the exponential expansion of space. Where matter was slightly denser, gravity pulled more material inward. Where it was slightly less dense, regions became voids. Over millions of years, this process compounded. Small overdensities grew into larger ones. Gas clouds collapsed. The first stars ignited. Galaxies began to take shape, drawing matter from vast filaments of dark matter that threaded through the cosmos like invisible scaffolding. This process had limits. Gravity operates at a finite speed. Matter can only fall inwards so quickly. Stars can only form when gas cools enough to collapse, and cooling requires time. Dark matter, which does not interact with light, provides the gravitational wells that attract ordinary matter, but it cannot collapse as efficiently as gas because it cannot radiate energy. Everything that forms in the universe is bound by these constraints, physical bottlenecks that determine how quickly structure can grow, how massive objects can become, and when they can appear in cosmic history. Cosmologists have modeled this process with extraordinary precision. They simulate the evolution of the universe from its earliest moments to the present day, watching as virtual particles cluster, collapse, and form the hierarchical structure we observe. Small galaxies merge to form larger ones. Massive black holes grow by accreting gas and consuming stars. The predictions these simulations produce match what we see in telescopes across billions of light years, except in one place. As we move deeper into the early universe, observing galaxies as they appeared when the cosmos was only a few 100 million years old, we begin to find objects that do not fit the timeline. Galaxies that appear fully mature too early. Black holes with masses that exceed what should have been possible given the time available for growth. These are not marginal discrepancies. These are systems whose existence implies either that our models of structure formation are missing critical physics, or that the early universe was fundamentally different from what we have assumed. The most extreme example of this tension is not a galaxy. It is not a cluster. It is a black hole. Black holes form when matter collapses under its own gravity to a point where escape velocity exceeds the speed of light. The boundary surrounding this point, the event horizon, marks the threshold beyond which nothing can return. Inside, space-time curves so steeply that all paths lead inward. Time itself becomes distorted, stretching toward infinity as seen by distant observers, but experienced as a finite interval by anything crossing the horizon. These objects are not exotic theoretical constructs. They are confirmed features of the universe, observed indirectly through their gravitational effects, the radiation emitted by infalling matter, and in recent years, through the shadows they cast against the glowing gas around them. Most black holes form from the deaths of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses in a fraction of a second, compressing matter to unimaginable densities and rebounding in a supernova explosion that can briefly outshine an entire galaxy. What remains behind is a black hole with a mass between a few and a few dozen times that of the Sun. These stellar mass black holes are common. They populate galaxies in vast numbers, remnants of stars that burned brightly and died violently across billions of years. But there is another category. At the centers of most large galaxies, including our own, there exist black holes with masses millions or even billions of times that of the Sun. These supermassive black holes did not form from single stars. No star can become that massive. Instead, they grew over time through a combination of gas accretion and mergers with other black holes. The process is gradual. Gas spirals inward, forming an accretion disk that heats to millions of degrees and radiates energy across the electromagnetic spectrum. Some of this radiation pushes outward, creating winds that can expel gas from the galaxy entirely, limiting how quickly the black hole can grow. Mergers add mass in discrete events, but each merger requires two black holes to exist in the first place, and for their host galaxies to collide and coalesce over hundreds of millions of years. This growth process has a natural pace. Even under ideal conditions, where gas flows inward continuously and no feedback mechanisms interrupt accretion, a black hole can only grow so quickly. The limit is set by the balance between gravitational infall and radiation pressure. As matter spirals into a black hole, it releases energy. That energy pushes outward on nearby gas, preventing it from falling in. The maximum rate at which a black hole can grow while radiating this energy is known as the Eddington limit, and it imposes a strict constraint on how massive a black hole can become over a given period. If a black hole begins as a stellar remnant with 10 solar masses and grows at the Eddington limit without interruption, it would take hundreds of millions of years to reach 1 billion solar masses. If it grows more slowly, interrupted by periods where gas supplies are depleted or feedback clears the surrounding region, it takes even longer. This means that supermassive black holes observed in the present-day universe, black holes that have had nearly 14 billion years to grow, are entirely consistent with this framework. But what happens when we look back to the early universe, when the cosmos was less than 1 billion years old? The first galaxies to form after the Big Bang were small, irregular systems, barely massive enough to hold on to their gas. Their stars were different from those in the present day, formed from primordial hydrogen and helium with almost no heavier elements. These stars lived short, violent lives, many ending as supernovae that enriched their surroundings with the first carbon, oxygen, and iron. Within these galaxies, the first black holes began to form, seeded by the deaths of the first generation of stars, or possibly by the direct collapse of massive gas clouds in regions of extreme density. These black holes would have been small, a few hundred solar masses at most. They would have begun accreting gas immediately, growing as quickly as the physics allowed, but still constrained by the Eddington limit, still bound by the time available. And yet, when astronomers pointed their instruments toward the most distant reaches of the observable universe, they found black holes that were already billions of times the mass of the Sun, existing when the universe was less than 1 billion years old. This should not be possible. The time between the formation of the first stars and the epochs when these black holes are observed is not long enough for them to have grown from stellar seeds. Even if they accreted gas at the maximum possible rate without pause, the mathematics is unambiguous. If you begin with a black hole of 100 solar masses and allow it to grow at the Eddington limit for 700 million years, you can reach perhaps 100 million solar masses, not 1 billion, not 10 billion. But the observations are equally unambiguous. One of the most extreme examples lies in a quasar designated as a seemingly random sequence of numbers and letters, a catalog entry that offers no hint of the cosmic anomaly it represents. This quasar, powered by a supermassive black hole at the center of a distant galaxy, shines with a luminosity that exceeds 1 trillion suns. It is so bright that it can be detected across billions of light years, its light stretched and reddened by the expansion of space, arriving at our telescopes as a faint point against the blackness. The light we receive from this object was emitted when the universe was less than 700 million years old, less than 5% of its current age. At that time, the first stars had only recently begun to illuminate the cosmos. The intergalactic medium was still transitioning from neutral hydrogen to ionized plasma, a process driven by the ultraviolet radiation from young galaxies. Structure formation was in its infancy. And yet, at the heart of this distant system, there existed a black hole with a mass exceeding 1 billion times that of the Sun. To understand why this is so troubling, we must consider the steps required to build such an object. First, a seed black hole must form. This could occur when a massive star dies, leaving behind a black hole of perhaps 50 or 100 solar masses. Or it could form through the direct collapse of a gas cloud, bypassing the stellar phase entirely and creating a black hole of several thousand solar masses. This second pathway is more efficient, but it requires specific conditions. A pristine gas cloud, free of heavy elements that would allow it to cool and fragment into stars, exposed to intense radiation that keeps it hot enough to resist fragmentation. Such conditions may have existed in the early universe, but they were not common. Assume the seed forms early, within the first 100 million years after the Big Bang. It begins to accrete gas from its surroundings, pulling matter inward and growing. But growth is not instantaneous. Gas must lose angular momentum to fall inward, spiraling through an accretion disk that heats and radiates. This radiation pushes back, limiting the inflow. Even at the Eddington limit, mass doubles only every few tens of millions of years. To grow from 1,000 solar masses to 1 billion solar masses in the time available requires sustained, uninterrupted accretion at rates that exceed what conventional models predict. It requires an environment rich in gas, with minimal feedback to disrupt the flow. It requires the absence of supernova winds, galactic outflows, or other mechanisms that might clear the region and starve the black hole. And even under these ideal conditions, the numbers barely work. But this quasar is not alone. In recent years, as telescopes have probed deeper into the early universe, additional supermassive black holes have been discovered at similar or even earlier epochs. Some exceed 2 billion solar masses. Some appear when the universe was only 500 million years old. Each discovery compounds the problem, suggesting that whatever process formed these objects was not rare, not a one-time anomaly, but a common feature of the early cosmos. This raises a more troubling question. If our models of black hole growth are correct, and the Eddington limit represents a true physical constraint, then these objects cannot have formed through conventional accretion. They must have bypassed the usual pathways. Either they began with seeds far more massive than stellar remnants, requiring direct collapse mechanisms that we do not fully understand, or they accreted gas at rates that exceed the Eddington limit, implying that our understanding of how radiation pressure and gas inflow balance is incomplete. Some researchers have proposed that the early universe contained conditions that allowed for super-Eddington accretion, scenarios where gas falls inward so rapidly that radiation cannot escape efficiently, becoming trapped within the infalling material and failing to push outward. Others suggest that massive seed black holes form through the mergers of dense star clusters, where thousands of stars collapsed collectively into a single black hole of tens of thousands of solar masses, providing a substantial head start. Still others invoke exotic mechanisms, such as the collapse of supermassive stars that never ignited nuclear fusion, or the direct formation of black holes from primordial density fluctuations during the first moments of the Big Bang. Each of these scenarios solves part of the problem, but none fully resolves the tension between observation and theory. What makes this object, this billion solar mass black hole in the infant universe, so significant is not merely its mass. It is the implication that something essential is missing from our understanding of how the universe transitioned from near perfect uniformity to the complex structures we see today. The presence of such massive black holes so early in cosmic history suggests that either the initial conditions after the Big Bang were more varied than we thought, with rare high-density regions that could collapse directly into massive objects, or that the physics governing accretion and growth operates differently in the extreme environments of the early universe. There is another layer to this mystery. Black holes do not exist in isolation. They reside at the centers of galaxies, influencing and being influenced by their surroundings. The mass of a supermassive black hole is tightly correlated with the properties of its host galaxy. Specifically, the mass of the central bulge of stars and the velocity dispersion of stars in that bulge. This relationship, observed consistently in the local universe, suggests a deep connection between the growth of black holes and the evolution of galaxies, a feedback loop where the black hole regulates star formation and the galaxy provides fuel for the black hole. But when we observe these early supermassive black holes, we find galaxies that do not always follow this relationship. Some host galaxies are too small, containing fewer stars than would be expected given the mass of the central black hole. Others appear to be forming stars at prodigious rates, building stellar mass quickly but still lagging behind the black hole. This mismatch suggests that in the early universe, black holes may have formed first, growing rapidly before their host galaxies could catch up. This inverts our usual understanding of galaxy evolution, where stars and black holes grow together, each influencing the other. If black holes can grow faster than their galaxies in the early universe, it implies that the seeds for these objects were in place very early, and that the mechanisms driving their growth were more efficient than anything we see in the present day. As we move deeper into the implications of these discoveries, we confront the limits of our cosmological models. The standard framework for understanding structure formation is built on a foundation of dark matter, the invisible substance that comprises most of the matter in the universe and provides the gravitational scaffolding for galaxies to form. Dark matter does not emit light, does not interact with electromagnetic radiation, and reveals itself only through its gravitational effects. Its presence is inferred from the rotation curves of galaxies, the motion of galaxy clusters, and the patterns imprinted in the cosmic microwave background. Simulations that include dark matter successfully reproduce the large-scale structure of the universe, the filamentary web of galaxies and voids that stretches across hundreds of millions of light years. They predict the distribution of galaxy masses, the timing of mergers, and the growth of clusters. But these simulations struggle with the small scales and early times. They do not naturally produce the massive black holes we observe in the first billion years. They do not account for the rapid assembly of stars in early galaxies. They require additional physics, mechanisms that accelerate growth or change the initial conditions. Some of this missing physics may be related to how gas cools and collapses in the early universe. The first stars, formed from pristine hydrogen and helium, without the heavier elements that act as coolants in present-day star formation. These stars were likely far more massive than typical stars today, burning through their fuel quickly and ending as black holes or exploding as supernovae that enriched their surroundings. The remnants of these first stars could have seeded the growth of supermassive black holes, but only if they formed in sufficient numbers and in the right locations. Other missing physics may involve dark matter itself. If dark matter particles interact more strongly with each other than currently assumed, or if they decay into other particles, the distribution and concentration of dark matter in the early universe could have been different, creating denser halos that accelerated the collapse of gas and the formation of black holes. These possibilities remain speculative, constrained by observations but not yet confirmed. What we are left with is a picture of the early universe that is more dynamic, more varied, and more extreme than our models anticipated. The discovery of these massive black holes at cosmic dawn has forced theorists to revisit assumptions, to explore new pathways for black hole formation, and to consider that the universe's early history may have been fundamentally different from the gradual bottom-up assembly we have long envisioned. But the existence of this object does more than challenge our models of black hole growth. It forces us to confront the nature of cosmic time itself. When we observe a quasar at redshift 7 or 8, we are not seeing it as it is now. We are seeing it as it was, frozen in the light that left it billions of years ago. The light has traveled across expanding space, stretched to longer wavelengths, carrying information about the state of the universe at that early epoch. What we observe is a snapshot, a single moment in the life of that object. We do not know what happened to it afterward. We do not know if it continued to grow, eventually becoming one of the even more massive black holes we see in the local universe, or if its growth was quenched by feedback from star formation, galactic winds, or the depletion of gas in its surroundings. This temporal disconnect means that our understanding of these objects is incomplete. We see them at a specific moment, but we lack the full narrative. We cannot trace their evolution forward to the present day, because the universe has expanded and evolved in ways that make direct comparisons difficult. The galaxies and black holes we see nearby have had billions of additional years to merge, accrete, and interact. The early systems we observe are separated from us not just by distance, but by cosmic history. And yet, despite this separation, the existence of these early supermassive black holes tells us something profound about the nature of the universe. It tells us that the initial conditions after the Big Bang, the distribution of matter and energy in the first moments, were not as uniform as we once believed. There must have been regions, rare but significant, where density fluctuations were large enough to seed the rapid formation of massive objects. These regions would have collapsed first, forming the earliest galaxies and the earliest black holes, setting in motion a cascade of structure formation that shaped the cosmos. It tells us that gravity, given the right conditions, can act with extraordinary efficiency. The same force that holds us to the surface of Earth, that binds the moon in its orbit, that keeps the sun from dissipating into space, can also compress matter to such extremes that it warps space-time into a black hole and can build structures of billions of solar masses in a fraction of the universe's current age. And it tells us that the universe is not static, not fixed, but constantly revealing new facets of its nature as our instruments improve and our reach extends deeper into space and time. The discovery of these objects has also shifted the focus of observational cosmology. Telescopes are now being designed and deployed with the specific goal of studying the early universe, of detecting the faint light from the first galaxies, the first stars, and the first black holes. The James Webb Space Telescope, with its infrared sensitivity and unprecedented resolution, has already begun to uncover galaxies at redshifts beyond what was previously accessible, revealing systems that are brighter, more massive, and more complex than anticipated. Each new observation brings new puzzles. Some early galaxies contain stars that appear older than the universe itself at that redshift, suggesting that star formation began earlier than models predict. Others show chemical compositions that indicate rapid enrichment, as if multiple generations of stars lived and died in quick succession. And at the centers of many of these galaxies, there are hints of supermassive black holes, growing in environments that should not yet have been able to sustain them. What emerges from these observations is a picture of an early universe that was far from quiescent. It was a time of rapid transformation, where the first structures formed quickly, where black holes and galaxies grew in tandem, and where the processes that would eventually lead to the diverse cosmos we see today were set in motion with surprising speed. But the most unsettling aspect of this object, this billion solar mass black hole in the cosmic dawn, is not what it reveals about the past. It is what it suggests about the limits of our knowledge. Physics, as we practice it, is built on the principle that nature is comprehensible, that through observation, experimentation, and mathematical reasoning, we can uncover the fundamental laws that govern reality. For centuries, this approach has proven extraordinarily successful. We have mapped the atom, split it, and harnessed its energy. We have traced the history of the universe back to a fraction of a second after the Big Bang. We have predicted the existence of particles and forces before detecting them, confirming again and again that the universe operates according to consistent principles. And yet, the presence of this black hole suggests that our comprehension is incomplete. Not wrong, but incomplete. There are aspects of cosmic evolution, of black hole formation, of the interplay between matter, energy, and space-time that we have not yet grasped. The equations we use to model the universe are approximations, powerful and accurate within certain regimes, but limited when applied to the most extreme conditions. This is not a failure, it is an opportunity. Every anomaly in science, every observation that defies expectation has led to deeper understanding. The orbit of Mercury, which deviated slightly from Newtonian predictions, pointed the way to general relativity. The constant speed of light, regardless of the observer's motion, forced a reimagining of space and time. The accelerating expansion of the universe, revealed by distant supernovae, introduced dark energy and reshaped cosmology. Each of these discoveries began as a puzzle, a mismatch between theory and observation, and each ultimately expanded the boundaries of what we know. The massive black holes of the early universe may be the next such puzzle. They may point toward new physics, new pathways for structure formation, or new aspects of gravity that only become apparent under extreme conditions. They may require us to rethink the initial state of the universe, to consider that the Big Bang was not as smooth and uniform as we assumed, or that the processes governing the first 100 million years were fundamentally different from those that followed. Or they may reveal something even more profound. There is a possibility, acknowledged but not yet proven, that the universe we observe is not the only one, that the Big Bang, which gave rise to our cosmos, was one event among many, and that other regions of space, separated from us by unimaginable distances or by barriers we cannot cross, experienced different initial conditions, different physical constants, or even different laws of physics. In such a multiverse, the presence of anomalous objects in our universe might be explained by rare fluctuations, regions where conditions happen to align in ways that allowed for rapid black hole growth, even if such conditions are vanishingly improbable. This idea is speculative, untestable with current technology, and lies at the boundary between physics and philosophy. But it illustrates the depth of the questions raised by these observations. When we encounter an object that should not exist, we are forced to ask not just how it formed, but whether our assumptions about the universe itself are too narrow. As we pull back from this object, from this single black hole in the distant cosmos, we find ourselves confronting a broader truth. The universe is larger than we comprehend, not just in physical scale, though it is certainly that. The observable universe spans 93 billion light years, containing hundreds of billions of galaxies, each with billions or trillions of stars, and an unknowable number of planets, moons, and other objects. But the true scale of the universe is not measured in distance alone. It is measured in complexity, in the richness of phenomena that emerge from simple initial conditions, in the intricate feedback loops between matter, energy, and space-time that produce everything from subatomic particles to galaxy superclusters. And it is measured in mystery. For every question we answer, new questions emerge. For every phenomenon we explain, new phenomena appear at the edges of our instruments. The universe does not reveal itself all at once. It unfolds gradually, layer by layer, each discovery opening new frontiers, each answer leading to deeper questions. The massive black holes of the early universe are one such frontier. They stand at the intersection of gravity, cosmology, and astrophysics, challenging our models, pushing the limits of observation, and reminding us that the universe is not obligated to conform to our expectations. It exists independently of our theories, indifferent to our equations, governed by laws we are still working to fully understand. And yet, we continue to look. Telescopes peer deeper into space, capturing light from galaxies that formed when the universe was a mere fraction of its current age. Simulations grow more sophisticated, incorporating new physics and refining predictions. Theoretical frameworks expand, exploring possibilities that were once dismissed as too speculative or too exotic. The work continues, driven not by certainty, but by curiosity. There is a kind of humility in this, in the recognition that we do not have all the answers, that the universe is vast and strange and full of surprises, that an object which should not exist according to our current understanding might simply be telling us that our understanding is not yet complete. This is not a comfortable position. It is easier to believe that we have mapped the cosmos, that the remaining questions are details to be filled in, minor refinements to a framework that is essentially correct. But the history of science teaches us otherwise. It teaches us that the greatest breakthroughs often come from confronting the things that do not fit, from taking seriously the observations that defy expectation, and from being willing to revise even the most fundamental assumptions when the evidence demands it. The billion solar mass black hole in the early universe is such an observation. It sits in our data, undeniable, confirmed by multiple instruments and multiple teams of astronomers. It cannot be dismissed. It cannot be ignored. It demands an explanation. And in seeking that explanation, we may discover something far more significant than the solution to a single puzzle. We may uncover new principles of cosmic evolution, new pathways through which structure emerges from chaos, or new insights into the nature of gravity and space-time. We may find that the universe is even stranger, even more remarkable than we imagined. Or we may find that the universe is exactly as it should be, and that our surprise stems not from any deficiency in nature, but from our own limitations, our tendency to project order and predictability onto a cosmos that is fundamentally wilder and more varied than our models allow. Either way, the presence of this object has shifted something. It has reminded us that the universe does not owe us comprehensibility, that the cosmos existed for billions of years before the first human looked up at the stars, and will continue to exist long after the last human has vanished, that we are not observers standing outside the universe, cataloging its contents from a position of detachment, but participants within it, shaped by the same forces, composed of the same matter, subject to the same laws. And it has reminded us that wonder is not a luxury. It is the foundation of inquiry. Without wonder, without the capacity to be surprised, we would never ask the questions that drive science forward. We would accept the universe as it appears, never probing deeper, never challenging assumptions, never seeking to understand why things are the way they are. The massive black holes of the early universe inspire wonder precisely because they challenge us. They stand as monuments to the unknown, beacons shining across billions of years, carrying information about a time and place so remote that we can barely imagine it. They tell us that the universe was once different, that the rules we observe today may not have always applied, or may not have applied in the same way. And they tell us that there is still much to learn. As our instruments continue to improve, as our theoretical frameworks evolve, we will undoubtedly discover more objects that defy expectation, more galaxies that formed too early, more stars that grew too massive, more structures that assembled too quickly. Each will be a thread pulling at the fabric of our understanding, revealing where it is strong and where it is weak, and each will be an invitation to look deeper, to question more rigorously, to refine our models, and expand our vision. This is the work of cosmology, not to provide final answers, but to map the terrain of the unknown, to chart the boundaries of what we know, and to venture beyond them, always aware that the cosmos is larger and stranger than we can fully grasp. The billion solar mass black hole in the infant universe is one landmark in that terrain, a signpost indicating that our map is incomplete. But incompleteness is not failure. It is possibility. It is the space where discovery happens, where new ideas take root, where the next generation of astronomers and physicists will make their contributions, building on what we have learned and pushing into territory we have not yet explored. The universe will continue to surprise us. It will continue to present objects and phenomena that do not fit neatly into our categories, that challenge our assumptions, that force us to think differently. And we will continue to respond, not with despair at the limits of our knowledge, but with determination to expand those limits, to build better instruments, to develop more sophisticated theories, to collaborate across disciplines and across borders, pooling our collective intelligence in the pursuit of understanding. Because in the end, the presence of an object that should not exist is not a refutation of science. It is an affirmation of its necessity. It is proof that the universe is not a closed book, already read and understood, but an open question constantly revealing new chapters, new mysteries, new depths. And it is a reminder that we are still at the beginning of this journey. The light from that distant quasar, from the supermassive black hole that should not be there, has traveled for over 13 billion years to reach us. It has crossed the universe that has expanded, evolved, and transformed in countless ways. It has passed through intergalactic voids and dense galaxy clusters, redshifted by the stretching of space, attenuated by dust and gas, until finally it arrives at a telescope on a small planet orbiting an ordinary star in an unremarkable corner of an average galaxy. And in that moment of detection, a connection is made. A connection between the most extreme object in the early universe and a species barely a few 100,000 years old. A species that has only recently developed the technology to perceive such distant light, to analyze its spectrum, to infer the existence of a black hole billions of times the mass of the Sun. This connection is fragile. It depends on instruments that are constantly at risk of failure, on funding that must be renewed, on knowledge that must be passed from one generation to the next. But it is also profound. It represents the universe becoming aware of itself, matter and energy organized into forms capable of contemplating their own origins, their own nature, their own place in the cosmic order. We are not separate from the universe. We are part of it. The atoms in our bodies were forged in stars that lived and died billions of years ago. The forces that govern the motion of galaxies also govern the chemical reactions in our cells. The same gravity that built supermassive black holes holds us to the surface of Earth. We are expressions of the same physical laws, temporary patterns of complexity in a cosmos that trends toward disorder. And yet, we are capable of something remarkable. We are capable of understanding, not perfectly, not completely, but genuinely. We can look at a distant point of light and deduce the existence of a black hole. We can measure the redshift of that light and determine how long ago it was emitted. We can calculate the mass of the black hole the luminosity of the quasar, the rate at which gas is falling inward. We can compare these measurements to predictions and discover discrepancies that point toward new physics. This capacity for understanding is not guaranteed. It is hard-won, built on centuries of effort, countless observations, and the willingness to revise beliefs when evidence demands it. It is fragile, vulnerable to dogma, to funding cuts, to the erosion of public trust in science. But it is also resilient. Each generation of scientists builds on the work of those who came before, refining methods, expanding knowledge, and pushing the boundaries of what is known. The massive black holes of the early universe will not be the last anomaly we encounter. They will not be the final puzzle. The universe is too vast, too complex, too rich in phenomena for us to ever reach a point where all questions are answered. There will always be objects that defy expectation, observations that challenge theory, mysteries that resist explanation. And that is not a problem. It is the reason we continue to explore. The presence of an object that should not exist is not a dead end. It is a beginning. It is an invitation to look closer, to think deeper, to imagine possibilities we have not yet considered. It is a reminder that the universe is not finished surprising us, and that our journey of discovery is far from over. So we stand here at this moment in cosmic history, aware of our ignorance, aware of the vastness of what we do not know, but driven by the conviction that understanding is possible, that the universe, for all its complexity and mystery, operates according to principles that can be uncovered, tested, and refined, that an object which should not exist is simply an object we do not yet fully understand. And we continue to look into the depths of space, into the earliest moments of cosmic time, into the hearts of galaxies and the cores of black holes. We continue to measure, to calculate, to simulate, to theorize. We continue to build telescopes and train new generations of astronomers. We continue to ask questions, knowing that the answers will lead to more questions, and that the process of discovery is itself the goal. Because the universe, in all its strangeness and beauty, in all its complexity and mystery, is worth understanding, not because it validates our theories, not because it confirms our expectations, but because it is there, vast and indifferent and full of wonders we're only beginning to glimpse. And somewhere, in the distant reaches of the cosmos, that billion solar mass black hole continues to exist, accreting gas, warping space-time, shining across the universe with the light of 1 trillion suns. It does not know it is anomalous. It does not care that its presence challenges our models. It simply is. And we, from our small corner of the universe, look out at it with instruments and mathematics and wonder, and we ask, how? The answer, when it comes, will not be simple. It will involve new physics, new observations, new ways of thinking about the early universe. It will require collaboration across disciplines, the integration of theory and observation, the willingness to revise long-held assumptions. It will take time, but it will come, because that is what we do. We confront the unknown. We grapple with the impossible. We find objects that should not exist, and we work to understand them, not because it is easy, not because it is comfortable, but because the alternative, accepting ignorance, abandoning curiosity, is unthinkable. The universe is vast. The universe is strange. The universe is full of objects that defy expectation. And we are here, part of it, products of it, struggling to comprehend it. And in that struggle, in that endless pursuit of understanding, we find meaning. Not in final answers, but in the questions themselves. Not in certainty, but in the willingness to revise. Not in the comfort of the known, but in the excitement of the unknown. This object, this black hole that should not be in our universe, is a gift, a challenge, a reminder that the cosmos is larger and stranger than we imagine, and that our work is never finished. It invites us forward into deeper mystery, toward greater understanding, always aware that each answer reveals new questions, and that the horizon of knowledge recedes as we approach it. And so we continue, looking outward, looking backward, looking deeper, seeking not to conquer the universe, but to know it, to understand our place within it, to recognize that we are, however briefly, however improbably, the universe's way of understanding itself. And that perhaps is the most remarkable fact of all.